Okay, we'll get started. Can everyone hear me okay from back there? Okay, yeah. When you're in the class, if you could just listen to my whiteboard rather than on your computer, just put the computer away because I'm going to be using a whiteboard a lot. Of course, it'll be captured by video for the distance learning students, and I'll be using the slides here, okay? And so come with a pencil, paper, take a lot of notes. It's a graduate class, so we're going to be doing a lot of concepts and ideas rather than just equations, formulas, plugging numbers, and so forth, okay? First of all, I want to make sure this is aerodynamics, right? Graduate aerodynamics class, 6015? Okay. Today I'm going to do two things to start the class. First, I'll go through a set of slides to tell you what this class is all about. Then I will go to the Canvas site and kind of walk you through the various parts of the Canvas site. After that, we'll get started in the class material, okay? Anytime you have questions, just raise your hand. You're not disturbing me. Ask me questions. And I'll also talk to you later in my slides how to get in touch with me and so forth. Everything I present here will be posted. We'll also have the videos of the distance learning class, but a lot of things are done in the whiteboard. That's why it's important for us to be interacting, engaging, so you can understand what I'm talking about and vice versa. I'm going to briefly tell you about myself and what this class is all about. A little bit about the deliverables and the grading policy I'll put on the whiteboard, and also how to access me, okay? As far as the resources to this class goes, it's just a Canvas site. Anything you need in the Canvas site, I will post it there. If it's a report, a NASA report or something else, I will also post it there, at least a link to that particular material, okay? So we don't need a textbook for this class, but if we had an undergraduate textbook, hang on to it. Our undergraduate students use a textbook by Anderson, Aerodynamics. It's got a lot of material. It's a 3,000 level class. But when I saw this class population, both who are here in section A and also section Q, and there are a few students in Q3, European, Georgia Tech Europe, I found a wide variety of background from all of you. Many of you were from aerospace engineering, so you would get bored if I just talk about undergraduate material. On the other hand, if I skip that and go directly to 3D material, which is really the primary focus of this class, those of you who are coming from a mechanical engineering background or some other background will get frustrated. What is all this symbol you're writing and so forth. So I need to use some kind of a balancing act. 2D is the foundation, 2D is the fundamentals, but 3D is the new material we are learning in this class, okay? So I'll try to do some 2D. Sometimes I'll say this is a prereq, please review on your own. Then I will build on that. The reason we are also reviewing the 2D is if you're planning to go to PhD, fundamental concepts like the PhD qualifier exam, they'll start you with 2D, okay? They will not start you with 3D, okay? It's not a baseball game where you throw your fastest ball, try to strike out the person. You try to do them some softball, let them feel comfortable, then you strike them out, okay? So that's what graduate quals do. So they need to know you have the fundamentals. So 2 dimensions are easy to see, easy to visualize, and so forth, okay? So it's going to be mostly a 3D course, but with some 2D material thrown in. Okay. So let me start with myself. I am a professor in this school. I came here as a graduate student like you all in 1973, okay, 53 years ago. My class was in room number 360. I am now located 3 rooms from there. So in all the 52 years, I have moved just the 3 steps, to my new office. And I went to work at Lockheed after graduating from Georgia Tech from 77 to 82. 2 of those years were as a postdoc on a contract from Georgia Tech to Lockheed. Lockheed gave the money. I spent there. Then from 79 to 82, I worked full-time at Lockheed Martin. After that, I came to Georgia Tech. I became what you call a senior research engineer for a couple of years. Then in 1982, I became a professor. For 43 years, I've been teaching classes, mostly of aerodynamics nature. But even after 43 years, my slides will still have typos, errors, and so forth. Okay, so they talk about, I think Leonardo da Vinci or one of those famous painters. Every picture will have a flaw in it. That's how you tell it's his picture. If it's a perfect reproduction without any flaw in it, then it's a forgery. Okay, so every slide in mine will have some typos in it. Occasionally a Hindi letter or a Tamil letter, my mother tongue also. Okay. So I'm in room number 363. You can reach me here, but the best way would be to reach me here in the class. The first 5 to 10 minutes, I'll write down what we did in the previous lecture, kind of a bullet form. Then I'll ask you questions, give you a chance to ask me questions on the homework and so forth. Then we'll go into the new material. Okay? So it's important that you get here early so that you capture that material, ask me questions. After the class, if I don't have any appointment, occasionally we have appointments, like next week we have the PhD quals going on, but I will be happy to meet you in the classroom or just outside in the hallway. Okay? You can also ask me some quick questions. I won't have the whiteboard, but I can wave my hand and give you an answer. Okay? Occasionally I'll say, please look at the video. I'm not blowing you off. Okay? That's because your question required a more in-depth answer, which I had done in the beginning of the lectures on the whiteboard. So you don't need to watch the whole video to see where did he answer my question. Usually it'll be in the beginning of the first 5 to 10 minutes. Okay? So I'm not ignoring you, but this is how we will do. So ask questions in the class for section A, and also catch me after the classroom, or make an appointment with me. I recommend that you use Teams, because Teams pings me, wherever I am, in the bathroom, taking a shower, or taking a nap, it beeps at me. If you send me an email on Canvas, sometimes I may not answer because I think it may be for my TA or grader. And also I'm teaching 2 classes under research. So I have over 200 students. So if everyone asks me on email, it's a little hard to answer. But Teams message is always staring at me. It's hard to ignore. So I'll try to answer it right away. We can also make an appointment, but that's a little harder to do with 144 students here, and over 100 students in my wind energy class, and about 10 students in the research class. So as much as possible, let's do it face to face, but do not feel like I'm ignoring you. Try to catch me and make an appointment to ask me questions. Another advantage of Teams is then if there's a common question all of you are asking, then I will post it on the class website. This is the question you had on homework number 1. This is the response I gave. So all of you will respond to it in the same common way. Okay? That kind of helps us. You may call me at the number. It'll transfer me to this number, and I'll do my best to answer it. But sometimes I'm in a meeting and so forth. It's a little harder to answer you right away. And then it scrolls off my screen, right? We all get a lot of phone calls, junk mail, and so forth. But Teams message never go away. They are always there. You also can see me on my website, a lot of the information about me, my publications, my research, and things like that. Okay. So I have taught a lot of different classes over a period of time. My specialty is helicopter, aerodynamics. I also a specialist in wind energy, and I try to teach classes in this area. But we also do a lot of design of aerofoil wings, in the incompressible flow regime, subsonic flow, transonic flow, not that much in supersonic flow. So we do a lot of research in this area. Are you all following back there? We don't need to use computer at all, please. Okay, if you could put the computer back, let's take a notes. Okay, all right, thank you. All right. So this is my area of research, and you will also see a list of students graduated in recent years and a lot of information like that. Okay. So as I mentioned to you, everything is going to be on Canvas. I'm going to be going over it a little bit. You all are familiar with it, but there may be some brand new students just joining us from as a graduate, fresh graduate students. I'll show you where everything is stored. And then we are going to have 5 to 6 homework problems and 2 quizzes. Okay, I'm going to post the quizzes ahead of time, at the time window. It'll be a timed exam, about 90 minutes to 120 minutes. It'll be exactly available. Let's say I say one Tuesday at 8 p.m. It'll exactly be available at 8 p.m. Then you'll be able to have 2 hours to finish it. Okay? It's completely open book, open notes. So that's why I want you to take a lot of notes. You don't have time to be watching videos and things like that. Put a date when I taught a material, write down. That way you will remember, what was done, because it's a long course, right? 15 weeks long. At the middle of the semester, we have already covered 8 weeks of material. It's kind of a little harder to remember. And I'm going to have 5 to 6 homework assignments worth about 30% of the course grade. So if you do homework, you get a credit in my class. Okay? And then the 2 quizzes will be 35% each, 70% for quizzes, and then the homework will be 30%. Like all graduate classes at Georgia Tech, if you get a 90 or above, it will be an A. If you get 80 to 90, 89, it'll be a B. If you get a 70 or so, it would be a C, and so you could kind of see where you are in the exams. Don't worry about the weighting in the Canvas shows. Just I'll take all your 6 homework, add them all together by the total number of points that I assigned to you. Then I will multiply by 0.3 to get the weight for the homework. I'll take your quiz grade. It may be out of 100. I'll multiply by 0.35 to get the grade for the quiz 1. Then the quiz 2 will be towards the end of the thingy. Then we add them together. Since we have 9 time zones, some in Europe, 8 o'clock in Atlanta evening would be 2 a.m. in France, okay, which may be a little harder for them. So for those students, I may set up a separate time window. Other than that, Section A and Section Q would do the exam on the same day, okay, same day. We don't have a 1 day delay or 1 week delay like we used to do in the old days between Section A and Section Q. In old days, they had to tape it. It was a magnetic tape. Then they had to transcribe it to a computer. Then they had to post it. It took a long time. Today, everything is instantaneously recorded. You have seen the YouTube videos, it gets recorded. By the end of the hour, they have access to the video, okay? So we don't need a separate times for the Q section and the A section. So this is what we will be doing. All right. So the course is going to be 3 parts, roughly 5 weeks each. The first part would be a very, very low speed flow called the incompressible flow, primarily focusing on inviscid flow, that means no viscosity. But doesn't mean the viscosity doesn't play a role that affects everything we do. But we do have a 6009, which is a viscous flow course. Some of you may be taking it. And there's another turbulent flow class called 6012. But I will talk about viscous effects here, but the primary focus will be the inviscid flow, but it will interact with the viscous flow, okay? So in the assignments, wherever I have a chance, I will say, this is what our inviscid theory says, but this is what's happening in reality, kind of try to tell you the difference between the two, okay? And if I go too fast, just stop me, ask me, I can very happily repeat it. Even in the next lecture, you can ask me, last lecture you asked me for this, I didn't get it, can you go over it one more time? I'll be very happy to do it, okay? It's no point in rushing through it, so you don't get an idea. A lot of these material, up to this part, we study in 2D, but these bullet items would be the 3-dimensional new material, okay? And I do not plan on having a lot of MATLAB programming or Python programming, but occasionally there may be some need to do a MATLAB program or a Python program, your choice, okay? I grew up with the Fortran world, so I don't understand either one of them. but we'll get somebody to grade your work. So there's going to be 1 or 2 assignments where you have to do some programming. All right. So the second 5 weeks would be compressible flow. Again, I will do 2D background undergraduate material, but then we'll talk about the slender body, whether it's a fuselage or an airplane with a highly swept wing that looks like a very slender, long thingy. We'll talk about how to model it in supersonic flow. Okay, that's what we will cover. Then we'll also talk about a concept called wave drag, and then how to reduce it, how to make these three-dimensional aircraft, supersonic aircraft, fly efficiently. Then finally, the last 4 weeks or so, we will do hypersonic flow. So it's going to be, we will be reaching the end of the spring semester, and a lot of these things can be only done by computational methods these days, CFD, but there are some approximate techniques that are still used in the early stages of conceptual design. We'll try to focus on those, okay? All right. So we will cover these, and then there's going to be, as I mentioned to you, 5 to 6 homework, and then there's going to be 2 quizzes. It's honor code applies. So please do not copy from somebody else's work. You'll get a 0, and then also if it is a very egregious, violation of the code, I'll ask you, why don't you drop the class, please, because I'm going to fail you in this class, okay? Same thing with AI, okay? Today, you can go to AI and ask, AI, I want to model this wing using this vortex lattice program. Could you run it for me, please, and give me an answer? It'll give it to you the answer, okay? Yeah, it'll give you that. But if you do that, you won't learn anything, right? Because when a year from now, 2 years from now, you'll be in an industry setting and in a lab, your professor or your boss may ask you, can you tell me what's going on here? You won't have time to say, let me ask ChatGPT and give you the answer, because you need to understand the fundamentals. So any indication that you're using AI tools, ChatGPT, Gemini, I don't know the names of them all, but our Canvas site will catch it. So you will be failed and then asked to leave the class, okay, because it's a violation of the honor code. Undergraduate, we go to a level of reporting you to the dean of students and so forth, which creates a bad record in your record forever. It's not a good thing to do. I'll just ask you nicely, you're using AI, it's not a good idea, okay? So please refrain from it, and also don't copy from each other. We use AI tools, that I tell you not to use, so we know exactly, which material is covered by who. So please do not do that. You are here to learn. If you have questions, ask me. I'll be happy to answer it. All right? So no AI tools, no course hero checks, plagiarism, everything else is considered a violation. So if you have really some questions, ask me. For example, you may be tempted to take a quote from a book and say, explain the concept, right, in an exam. Let's say I'm asking you, explain what causes the induced drag. It'll be tempting to say, okay, this is what I learned in my undergraduate, let me copy it and put it in the code. That's a violation. We are asking you to demonstrate to me that you have captured the physics behind it, the ideas behind it, so we should not be copying and pasting, okay? So it's very important. I don't want your graduate students, you have been in the school for a long time, so I don't want to belabor the point. Again, for section A, please come to the class regularly. First 5 to 10 minutes, we will review the material, answer your questions. After the class, I can stay outside if I don't have any other appointment, okay? Next week, I'll have a bunch of qualifier exams to give. They start at 10 or so 9:15 I need to go to my office, because the exam is in my office. I need to clean up the place, get everything ready for the students and also for the other professors. How about the section Q and Q3? They can also ask me questions on Teams just like you are doing. But because they cannot ask me questions face-to-face here and also outside the classroom, I will make preferentially make an appointment with them to answer it. Okay. Sometimes it may be a 1 minute, get on a Teams and ask. Other times it may be 30 minutes, right? But I may also tell them, please see the video in the beginning of each lecture. I'm covering this. Your question has been answered. They should not feel ignored either because it's been responded. It's been covered. Okay. So this is how we are going to be accessing me. Okay. Any questions so far on the course or on the concept? Okay. Just to take a quick poll, how many of you come here with an aerospace engineering background? May raise a hand either here or from outside. Okay, great, already. Put your hands down. I'll give them a tougher exam, okay? How many of you have mechanical engineering or some other background? Okay, I see some people raising hands twice. Okay, no, just kidding. Okay, so I'm going to cover some fundamentals, but for mostly new material, okay? But hopefully there'll be enough foundation laid so that you can understand it. All this material will be in the class, including this set of slides, okay? So let's go to the class website. This is our class website. It's a combined website for A section, Q section, and Q3 section, okay? We have one grader. He's going to be doing grading only. He's not a TA, okay? A grader means his job, his name is Lander, just to grade your homework, post the grades. But he cannot be going back and forth with you, negotiating points and so forth. So he will probably tell you, please talk to Professor Sankar about this loss of points, raise this up with him. Then you and I will talk about it, okay? We can do it in the class or after, not in the classroom when many people are watching us, but outside because I don't want them to be hearing them yelling at me or vice versa. So we'll do it in the privacy in the hallway, okay? So, but anyway, TA, there's a grader who will be doing it. So all the material will be posted in here. Anything that's got a prereq, I expect you to read it on your own because I won't be able to spend a lot of time covering that also. For example, this afternoon when I get back to my office, I'm going to post our first assignment where we are going to be looking at how to model some aerofoils using a software called Xfoil. Okay? So all the material would be there, and my undergraduate video would be there, okay, a long time ago made. Probably during the COVID era, you'll see me covered in blanket and coughing, profusely. But fortunately, you are from behind the screen, so you won't get infected, okay? And maybe your computer will get infected, but that's a different story. So all of these things will be given there. So you need to kind of review this and start looking at it, the assignment number 1. I have not posted the exact wording in the assignment yet, but I'll be posting it this afternoon. It'll be due probably on a Sunday, not this Sunday, but the next Sunday, okay? Sunday night, okay? So today is 12, then the 25th night. Usually I put everything on the Sunday night because all the football season is over. Your teams have all lost, so you have no excuse other than to do the homework, okay? So you have to turn it in. But please don't ask me Saturday morning, how do I do this? Because my teams have not lost yet. I'm watching the game, so I'm not going to answer your questions, okay? You need to ask me during the weekday because all of us have lives. It's hard to be getting on the teams and answering you. So try to do it during the weekdays if you don't mind, okay? And do a little bit at a time so you get it done, so you don't need to worry about that pulling an all-nighter on a weekend, okay? That's what we would do. All right. So there'll be some prereqs. So the first part of the course, as I mentioned to you, deals with a lot of undergraduate material. Then we'll cover some new material for graduate material and so forth. So everything will be posted here. And sometime later, you may start seeing the videos here. I'm not sure exactly where it is, but somewhere here, you'll start seeing the videos that are recorded for this particular class, posted. I'll find out and then I'll let you know, it should be posted. Media gallery is where the lectures would be posted, okay? But please come to class because we will do a lot of interaction, ask you questions. If you feel it's an 8 o'clock class, let me watch on video. It doesn't make sense because we miss that interaction, okay? And then if you ask me to make a one-on-one, I may be less reluctant to make appointment with you. I will say, come and see me in the class tomorrow. We can talk. You know, it makes it harder for you, right? So come to the class and do it. So this is how things will proceed. So anytime something is a prereq, I'll try to label it as a prereq. And then I'll put some video lectures and different things along the way. So this is how we'll do. For example, all of this is a 2D material. So anytime I already have a video posted here, it's an undergraduate material. Okay? Not to say I won't cover it here, but perhaps not in the same depth, because our undergraduate course is a 4-credit-hour course, AE 3030. If I spend all my time talking about it, then we won't learn anything new. On the other hand, I don't want to ignore everything either, right? So we have to balance it. I may not always strike the perfect balance. When we review the class, some people say, I got so bored because he was teaching the same thing I learned, the same bad jokes about Leonardo da Vinci, so type of thing. Others said he went way over my head. We don't need a computer. Can you put the computer down, please? Hello? We don't need the computer, okay? Take notes. Take a piece of paper or a tablet is okay. You can write on it with a pen. That's fine. Okay? Please pay attention. Don't be doing something else. Okay? In the class. Okay? All right. All right. So how about the assignments? I'll post all the assignments here. They are not on yet, but I'm going to be turning on the assignments. Okay? I have not decided exactly how to do it. I'll also post the quizzes there, but they'll become visible exactly the minute when it's due. Okay? So by tomorrow or maybe by Wednesday, I'll already post you the first quiz date, okay? Most likely it'll be at 8 o'clock in the evening, okay? And 8 to 10 or 8 to 9:30, okay? And then for the Q3 section, I'll come up with a different time window, okay? And you can take the exam from your apartment, your home, wherever you are. But don't work as a group on the exam, okay? That's an honor code violation too, okay? Work independently, and that's what we would do. Then the second quiz would be here. Don't pay attention to these dates and so forth that may show up. They are from a previous generation, in a previous year. So we are going to be changing it, all right? And all your grades will be posted in the grades section. All the announcements would be posted up here. Right now there are no announcements, right? So usually as soon as I post a homework, you'll get an email saying homework 1 has been posted, right? And then likewise, when my TA or a grader posts a grade, you'll get an announcement. If there's a clarification on your homework, I will post it over there. As a reminder to your exam, I may post in the announcements. I'll also post a study sheet, how to prepare for your exam, here on the announcement section. Okay? So just keep an eye on the announcements, keep an eye on the resources, keep an eye on the assignments, keep an eye on the grades. Okay? And then everything you need will be down in here. Then towards the end of the semester, I'll ask you to do a course survey. There'll be something called CIOS, and that's where you go and survey this class. By the way, occasionally we may need to have a Zoom meeting. Either I'm not available or I'm on travel. I'll send you plenty of notice ahead of time. We're going to be on Zoom this day. Here is the link. You'll get a link to that. Okay? So I'll try to be as clear as possible. So this is all, we are going to, just an overview of our course. Are y'all okay with this? Any questions so far? All right, thank you. So let's go to the very first lecture. I'm just going to start with the properties of the fluids. So let me start doing it on the whiteboard. Okay. This is an aerodynamics course, so we are going to deal with the air as the primary molecule. And it's really a mixture of different species, right? Nitrogen, oxygen, hydrogen, you name it, other species, is a mixture of different gases. Okay. So even a very simple thing like a P equal to rho RT, which is the equation of a state, this R depends on the composition of the gases. Okay, if you have a 70% nitrogen, it's going to have a molecular weight 28. If it's got a say 15% oxygen, it's going to have a molecular weight of 32, and so forth. So they have to weight the molecular weight properly. So this R, for example, is called the gas constant. Of course, the books like Anderson may give you a number 287 followed by some units. But that 287 came from some universal gas constant divided by molecular weight. So this is a universal gas constant. This is the molecular weight. So the molecular weight is determined by how much nitrogen there. You'll have a higher weightage toward the molecular weight than oxygen, than other species, depending on their mass fraction. Okay. All right. Now, how do we keep track of it? 1 mole of gas, example, 28 kilograms of N2. Where does N28 come from? It's the molecular weight. Okay, so 1 mole means 1 molecular weight worth of gas in kilograms. If you count the molecules, you'll have a roughly 6.023 times 23 or 10 to the power 23 molecules. This is called the Avogadro number. Nobody questioned him, nobody went and counted that, but if you take the molecular weight and divide it by the molecule of the individual molecule, we know how much hydrogen atom weighs, how much oxygen atom weighs, and so forth. So we can find the number of molecules, then this is what we get, okay? Universal gas constant. So this room, if I take a 28 kilograms of nitrogen, then I'm going to have that many molecules. So keeping track of the individual molecules is a very hard thing to keep track of. So way out in outer space, in higher altitudes, where the satellites are flying or the space station is flying, so in the outer edges of atmosphere, these molecules are spaced far apart. So there's one molecule here, one molecule over there, kind of a very sparse molecule on the outer edges of the atmosphere. Eventually you get a complete vacuum, there's not any molecule there because they are attracted by Earth's gravity force. So there is this molecule surrounding it, then you have a total nothing there. Right? Now, the average distance they travel before they collide with each other before collision is called the mean free path. Okay. So I'm going to give the symbol lambda in meters, will be called the mean free path. Can you all see back there? Am I writing it okay? All right. So in this room, for example, mean free path is of the order of a meter in the first row, of the order of a half a meter or less than a meter, second row. 2 centimeters if it's a Delta airplane, flight, okay? If it's this room, lots of molecules are bumping into each other very closely because they are tightly packed, okay? Lots of molecules. So we use a criterion. We take the vehicle length, representative length, doesn't matter whether it's a fuselage length or a wingspan, some representative length. Then if you divide by this mean free path, as long as this is in the same units, meters and meters, it's going to cancel. We'll get a non-dimensional number. That number is called, some people call it Knudsen number, some people call it Knudsen number. So this is the number. Okay. Are you all able to see this okay back there? Okay. Shall I lower this one down? Okay. How about now? All right? Okay. So this is called a Knudsen number. So if Earth here, in the lower atmosphere, L over lambda is very large. Why? Because this is like a 10 to 20 meter long vehicle, maybe 30 meter long vehicle. This is of the order of a micrometer, so it's a huge number. Then we should use what we call a concept of continuum, treat it as a continuous fluid. There's not a little bit of very little space between the molecules. They bump into each other and they equalize their behavior. Have you been to, if you have done a Peachtree Road race, for example, at the beginning of the race, even the fastest sprinter cannot run 6 miles per hour when the clock starts because there are people around them, right? So he or she will bump into the others, then they will slow you down. In my case, usually people behind me saying, get a move on, brother, pushing you. But all of you have the same velocity. In other words, when you're bunched together. So concept of continuum, what we are going to do is, we are going to average the velocity of all the molecules and then treat it as some average velocity. Okay, so that's called the concept of continuum applies. So if L over lambda is greater than 1, treat air as a continuous fluid. I'll explain a little bit more. Fluid. Use average velocities of molecules. And average properties of the molecules, okay? Not just the velocity, but the energy, whatever it is. So we are going to use average properties of the molecules. So when we use a pressure gauge and pressure maintain the pressure, or when we use a pitot tube and measure the velocity, we are talking about not individual molecule, but thousands of molecules. They're all bumping into each other, therefore they all have the same average velocity. But in the outer space, this molecule is not bumping into this one, so it's going its own merry way, this is going its own way, there's no reason. So in the outer edges, you'll use what you call a molecular dynamics, okay, which is a different, you can treat it as an individual molecule. You can use a Newton's laws of motion. Here is a rubber ball I hit against the wall, rate of change of momentum in the physics type of a thing you could do, individual treatment. Okay? So this is called the concept of continuum. Therefore, let me start with my very first set of slides which talk about these properties. Okay. Can you all see this okay? The concept of continuum is basically air is made of a lot of molecules. If they are packed together, like here on the lower Earth, because we have a distance is small compared to the vehicle length or the reference length, then we can assume some average properties prevail, such as velocities and temperature. Then we can treat the collective average values rather than the individual molecular velocity, because there are far too many of them to keep track of. So this is called the concept of continuum. Okay? So that's what we'll be using in our course. But we do know that on the outer space, you could deal with individual molecules, rarefied aerodynamic atmosphere. You can do individual molecules. So when you have a space station with its solar panels opened up, sometimes they may experience a drag because the molecules bump into it, slowing it down. Okay? So those type of things you will use some molecular dynamics. But in our course, we're going to use the concept of continuum. So what are the properties of the fluids that we want to work with? The first thing is density. Density is pretty straightforward. It's just a kilograms per meter cubed is the mass of the fluid. We will use a British system of units for the most part, but sometimes people will use a British system of units, so the correct mass that you have to use is slug per cubic feet. Okay. So what is one slug? One slug is 32.2, roughly G times pound mass. Okay. So when I go to my doctor annual physical, every year they ask me how much do you weigh. For the past few years it's been creeping up, so 150, 160, 165 and so forth. So I have started saying I weigh only 5 slugs, so that kind of keeps my doctor happy, me happy. So 32.2 pound mass is 1 slug. Okay. So 1 pound force, when we talk about pound force, F equal to ma, we are either going to use a Newton or we are going to use a pound force. So 1 Newton, we will usually just use the letter N, would be 1 kilogram, F equal to M times A. So when we do the pound force, it's 1 slug times 1 feet per second squared. Okay? So when I go report my weight, if I say 5 slugs, example, times 32.2 will be 161 pound force. That's how much I'm weighing. Okay? So whenever you have to use a density, you have to be careful with the units. Okay? Don't directly plug in the pound mass, convert that into slugs. P equal to rho RT, for example. Rho has to be in the proper units. It's always a good idea to write the units and see they cancel. Your high school, your undergraduate professors would have stressed those things. It's very good practice to cancel the units, make sure they cancel. Okay? So this is what it is. Now pressure is just a normal force per unit area. P is always on a surface. It always acts normal to the surface. And it's got a units of, it's a normal force per unit area. So it's got a Newton per meter squared or pound force per feet squared. Meter or feet. Okay, we won't use the inches. PSI, for example, we use, right, by pounds per square inch. Multiplied by 144 inches squared is 1 square foot to get this. So again, it'll be pound force per square foot Newton per meter squared. It's always a normal force. So where does this force come from? It's those molecules bumping against our body, pressing the force. Okay. So why don't we collapse, when all this pressure is acting on our body? Because internally our body is pushing against it, kind of balancing it. All right? What would happen if you go to outer atmosphere where there is no molecules? Your internal pressure will push your skin outwards because there's nothing to balance it. Then it's going to break apart. Okay? So anyway, pressure is the second thing. The temperature is the third thing. It's a measure of internal energy of the molecules. So E is called internal energy. But we will use the prefix specific all the time. Specific always means per unit mass, okay? Per unit mass. So the molecules have an internal energy. Not the kinetic energy, which we are going to talk about separately. They may have a velocity u, v, w in three directions. 1/2 u squared plus v squared plus w squared would be kinetic energy, right? So in a wind tunnel, if the air is flowing from left to right, if you measure the velocity, the energy, kinetic energy associated with that velocity is 1/2 of u squared plus v squared plus w squared. Okay. So that's a kinetic energy. But internal energy is caused not by this organized motion of the velocity of the molecules, but the random motion of the molecules. Okay? So the diatomic molecules which we have normally can have three linear velocities in the x direction, y direction, z direction. Randomly, okay, they are going this way and they are going this way, they are going up and down, they are going left and right. But they have energy associated with it. Although their average may average to zero, in a dead still room, if you look at somebody asks you what is the velocity here, you may say it's zero. But it doesn't mean the molecules are not moving there. They are just randomly moving, average out to zero. But they have kinetic energy associated with this random motion, right? Because they have a u squared, they have v squared, and they have w squared in the three directions. Okay? So that's three components are there. But then they can also rotate, in this about this axis. Like if I have one molecule here, it may do like this, right? It's like you do it. I used to demonstrate it, but after 2 surgeries, I no longer do that. Okay, you just believe me, you can rotate this way. Then because the masses are far away from the axis, it's got a huge moment of inertia so that they can spin that way. But these molecules can also spin about a vertical axis, in and out of the plane of the paper. It can come out of the plane of the paper, go into the plane of the paper. So it may spin like this, okay? So come out, go out. So that's another degree of freedom. So you get two rotational degrees of freedom. How about the third axis? If you look at this, it won't have much moment of inertia, okay? Because the center of gravity is right on the axis. So no matter how fast it spins, it's not a lot of energy. So the third mode of energy is not that dominant. So we get 5 degrees of freedom. So these are the 5 ways energy is expressing itself. Sometimes we use the word degrees of freedom. So 3 linear random motion and 2 rotational motion is what causes it. Okay? So the internal energy expresses itself in these 5 different ways, and Mother Nature equally distributes it in all the 5 ways. Each random motion, x, y, z, have the same amount of energy, rotation has got the same moment of energy. So this is what happens in a normal lower temperatures. Okay? Then we can say dE, for example, some specific heat times temperature, where the CV is called specific heat per constant volume. Have you heard of this before in thermodynamics? Regardless of your major, you would have seen specific heat, right? Holding volume fixed. So if you change the energy by raising the temperature, the internal energy will change. So CV will be a constant for our purposes. Okay? But as you go to higher and higher temperatures, for example, we are going to talk about a hypersonic flow in our class later, then there's so much energy that these atoms start vibrating. Okay? They will start moving back and forth, want to break apart. So one atom here, another atom here, whether it's a nitrogen or oxygen or whatever, as temperature goes up, it may act like a spring mass system. They want to break apart, but then the electron attraction to the proton bring it together. So they're going like this, like a yo-yo, they're like a two springs. Okay, so there's some energy associated with it. So this occurs only at very high temperatures, not in our room temperature that we are talking about, or even a few hundred degree temperature, degrees Celsius doesn't happen. You have to have thousands of degrees of Celsius before this begins to manifest itself. So in hypersonic flow, when the temperature gets very high, we may need to worry about these things. Okay? So this is called a vibrational degree of freedom. That means it starts vibrating. And continuing with the temp T goes higher, they may dissociate. Dissociate means that they break it into atoms. One hydrogen atom, the bond is too weak to withstand that energy, they break apart. And if the temperature goes even higher, then they may ionize. Ionize means the electrons may fly off the handle surrounding the atoms. So you may have a negative electron floating about here, and a positive hydrogen ion floating out here. It becomes an alphabet soup of positively and negatively charged ions and electrons. It becomes a plasma. Okay? So when all of these things happen, your CV is no longer a constant, 5 degrees of freedom. Here, CV becomes a function of temperature. It's no longer a constant. But at higher temperatures, when things start dissociating it, it may also become a function of not only the temperature, but also the pressure. Why pressure? Because if you have a high pressure, they don't want to dissociate so much. Dissociation is suppressed because of the pressure. It's like mom and dad pressure, keep the family together, but when they are not there, it breaks apart, right? That type of thing. So, crude analogy. So now, when this happens, we call it a thermally perfect gas. Here we call it a real gas. If CV is a constant, then we call it a calorically perfect gas. Have you seen these terms before? Have you all seen this before? If not, review it, thermo. So a calorically perfect and a thermally perfect gas is sometimes called a real gas. Ideal gas. Okay? So sometimes you will say ideal gas law. CV is a constant. Later on we're going to talk about CP, specific heat at constant pressure. That's also a constant. So at the room temperature, we have a calorically perfect gas, thermally perfect gas is a perfect constant. At hypersonic flow, initially it becomes thermally perfect gas. At an even higher temperature, it becomes a real gas. So when a space shuttle was re-entering the Earth atmosphere, or some of those rockets that we see, when they re-enter Earth atmosphere, they are experiencing real gas effects surrounding plasma. This was a big area of research in 1970s, 60s, when the Russians and the Americans were trying to come up with ICBMs. They wanted to know what happens when these things go up in space, come back to the Earth. So there was a lot of research. In the 80s, remember, space shuttle was built, so there was a lot of interest in what happens, because now we are not just bringing missiles to Earth, we are bringing human beings back to Earth, so we need to study. So a lot of research went to it. Our school, we have a professor, Steve Ruffin, he's a professor. He spent his thesis working on real gas models for air, for a variety of temperatures, pressures, and so forth. Do you all know Dr. Ruffin? Have you heard of his name before? Anybody? You will come across his face, much younger than me, much better looking. His only fault is he's a New Orleans Saints fan, so, we don't talk to each other during football season, but starting tomorrow, we can talk to each other, okay? He went to his bachelor degree at Princeton University. He did his master's at MIT. He did his PhD at Stanford. Then he saw the light and he came back to Georgia Tech to teach. Okay, so he is our colleague here. So sometimes tell him, can you tell me about your research? So this is what he will talk about. So in hypersonic flow, we have to worry about this. So one of our assignments, I'm going to give you flow over a wedge or a cone, and I'll ask you to use an ideal gas and real gas and see what happens. Okay? In the exam, I may give you a normal shock wave and say, what happens behind the shock wave using ideal gas? What happens behind the shock wave using real gas? Can you do that? Okay? So we'll see the differences there. But the first 5 weeks, incompressible flow, we are not going to worry about even density is not changing. We are not going to worry about temperatures. We are only going to be worried about the pressure, the 3 velocities. But the second part of the course, compressible flow, density will change, temperature will change, velocity will change, but it will be a calorically perfect gas, thermally perfect gas, therefore an ideal gas. Then the last part of the class will be a real gas. Okay, so that's how we will be dominating the 3 things. So these are the properties of the gases. So we need 6 equations, right? P, rho, temperature. This is the organized velocity. That means you take thousands of molecules, average their x velocity, that's what you call U. Thousands of molecules, average their y velocity, that's called V. In the z direction, that's called W. Okay? So that's an average property. That's where we mean by concept of continuum. We take a collection of bundle of molecules and find their property as an average. Okay? All right. So we need 6 equations. So one equation is the equation of state, which is P equal to rho RT, but the other 5 would be, Knudsen number is upside down, lambda over L, not L over lambda. Lambda is the mean free path, distance traveled before collision. L is the vehicle dimension, could be the length of the fuselage, could be the span of the wing. It's just a reference length. We are only looking at the order of magnitude, not precise numbers. At low altitudes, Knudsen number is very small. Concept of continuum applies. At higher altitudes, we have to treat them separately. Right? Now, we are going to talk about streamlines in a minute. Okay? Then we are also going to talk about later on Navier-Stokes equations and so forth in a minute. But I want you to get started with the first assignment, which I'm going to post later on today. So I'm going to go to the section on aerofoil and quickly review that. Okay, for the next 10 minutes or so, we'll be reviewing it in here. So let me go to the introduction to aerofoils, which is an undergraduate material. Let me download it here. Are you all able to see this okay? This is introduction to aerofoil. This is a basic freshman material, but I'm going to kind of quickly go over the background. Because the first assignment, we'll be dealing with the aerofoils. We are going to be computing their properties: lift coefficient, drag coefficient, pitching moment coefficient. I'm going to ask you to look at 3 different aerofoils and comment on why do they behave differently. Although they are all the same thickness, why is one behaving different than the other? Okay, we are going to look at it. All right? So we are getting ready for it. So I'll introduce you to some notation, naming convention, and then the forces and moments, and then talk about it. Of course, the aerofoils are used not only on airplane wings, but also on propellers, helicopter rotors, turbofan that push the turbofan aircraft that you came in maybe from California or from India. Inside the compressor of an axial compressor, you'll see many stages. Some of them will be rotating, they call the rotor. Others will be stationary, we call them stator. If you slice them, it'll look like an aerofoil-like shape. Okay, so they are very ubiquitous everywhere. Turbine blades, same way. Hot gases come from the combustor. They go through this row of blades, rotate them, producing a torque, producing the power. Some of the power is used to power the compressor. The rest of it is used to power the turbofan to give the propulsion. Okay, so that's how the turbofan engines operate. Okay? So again, those are aerofoil-like devices. Hydrofoils are aerofoil-like devices, but they are usually found in a boat. Sometimes some boats will have underneath it like a wing immersed in the water. So as they go very far, very fast, that the wing will want to lift up. So basically the whole boat will rise a little bit above the water line. The more immersed it is in the water, more the drag, more the water resistance. So the more it lifts up off the water line, there's still a part of it is under the water, so there's some resistance there. But if you put too much lift, they will go up and down. You may have seen some boat bouncing up and down in the water, just about ready before they flip over. Okay, so they are powered by hydrofoil, which is a passive wing-like device, so that produces lift. But anything that produces lift also has got a drag. They can also experience a torsional moment because of the distribution of the pressure. Okay, so you may have more pressure here, less pressure here, then the body may want to rotate this way, and vice versa. So we need to understand it. Wind turbines, my class, I teach from 2 to 3:15 this afternoon. They use the aerofoil, okay, for producing power. Okay, so it's a very ubiquitous thing. So we need to know how to model them, how to understand them. So when 1870s or so, people started building gliders, and they started flying them. Aerodynamics or fluid mechanics is very old. You may know that Newton is the father of modern mechanics. In the 1700s is when Newton was alive, right? He performed his equations of motion. He also came up with the orbital mechanics, elliptical, Kepler's law, mathematical verification using his gravitational law. He did a lot of different stuff, but nobody had any idea what fluids is all about at the time. Then in the 1800s, 2 people came. One is called Euler, Swiss scientist. Bernoulli. Have you all heard of a Bernoulli equation? How many of you have heard of Bernoulli equation? Can you see a show of hands? Okay. I was going to say you heard it here first, but I guess everyone has heard it, right? Bernoulli equation. Euler, Bernoulli were like 1800. That's when they came up with pressure, velocity, relationship is a Bernoulli equation. We're going to talk about later. Then in the 19th century, people started building stuff and either jumping off the cliff or run down the hill and see if they can float. Some lived to tell the story from a hospital bed. Others, it was written on their tombstone, when exactly they flew. At least we had a historical context to what happened. Okay. Then the Wright brothers came along. By the way, Navier-Stokes equations were developed at the beginning of the 20th century, I would say 1890 to 1904, 1905. In the time window, Navier, French guy, Stokes, Irishman, they came up with Navier-Stokes equations. You will read more about it in 6009. In our class, we will introduce you to that. Then the Wright brothers, they were smarter. They didn't build and jump off the cliff. Only towards the end of it they did. They were bicycle mechanics. They were very good with the hands-on things. So they started building a small wind tunnel, blow air through it with a fan-like device, put a little model and test it. So they said, if I make my foil very, very thin, parafoil, you see the people over the California coast, they go like this, then they eventually land, hopefully on the sand, not in the shark-inspected water. So they are using a very, very thin foil. Wright brothers realized if I flip the angle a little bit higher, immediately over the upper surface, the flow stalled or separated. I have a video here called Stall. I encourage you to view it, please. It's a prereq material. He talks about stall, when you pitch the airfoil up. So Wright brothers, they were still using fabric-like material, but they blunted the leading edge a little bit, make it a rounded leading edge. It had a better stall characteristic. Not a whole lot. 5 degrees to 10 degrees, it was able to fly if you pitch up or pitch down. Okay, it was okay. But it had no strength to it, right? Because it's a fabric, just like my shirt. So how do you reinforce a wing? They knew how the houses are constructed, box-like structure, right? You put 2 pieces of a rod, connect it with another rod, then it becomes a stronger structure. So they had upper wing, lower wing, braced by rod-like structures along the wing, connected by wires crisscrossing each other, and they were all producing a rigid structure. But they had a huge amount of drag. Later on, I'm going to show you that a cylinder of 1 millimeter and an airfoil of 1 meter are going to have the same amount of drag. Okay? That's because the cylinder is a bluff body, not a streamlined body. When the air goes over it, it kind of separates it, produces a lot of drag. So since they had a lot of crisscross wires and they're strung out, huge amount of drag. They had a landing gear sticking out on the ground, so that had a huge amount of drag. But they were not worried about it. They just wanted to get off the ground and set a record. They knew these things will evolve. So they had a bracing upper and lower wing. But then later on in the 1930s, after the First World War, 1918 was over, people got interested in research. NASA finally got into the act in the United States, NACA. Europeans, Göttingen, France, Royal Aeronautical Establishment in England, you name it, Germany, other places, they started building wind tunnel and testing it. So they found if I can make it a conventional airfoil shape that we now know, we can internally provide the structure strength for bending and torsion. We can get away with a single wing. We don't need a biplane wing. So that's how it evolved. But the World War I fighting aces, they were not going to get on a mono wing plane. They said, where is my biplane? I was getting twice the lift. Now you're robbed me of half my lift. I'm not going to get on that. Okay. And also the cockpits were closed with canopies at the time. Before that it was open cockpit. If you have seen Indiana Jones movie, The third movie, the father is shooting, with a gun, head sticking out. That's what the pilots liked it. They wanted a 360-degree view so they could move their gun around and hopefully not hit the vertical tail in the process and shoot. Okay. But then when you put a canopy, then the drag went away. Okay. Then if you tuck in the landing gear inside, then the landing gear drag went away. Then whole engines, aircraft engines were exposed to the air cool them. Think of your car as the hood open, wide open. You may have seen some old generation cars. Everything is out in the open because that's the only way you air cool it. But then NASA found if you put a cowling or a covering around it, you can still force the air to go through it, just like in a car. The radiator, air goes through it, cools the engine. You can reduce the drag. So all those importance came along later, but the Wright brothers came up with a rounded, blunt leading edge, and then later on these people came with an airfoil. So I'm going to continue with this on Wednesday, but I want you to please start. Don't wait till Wednesday. A lot of these things we have the videos available. We have different things posted here. Start becoming familiar with it. You don't need to memorize everything. We are going to talk about the streamlines vorticity later on. But for the homework number 1, aerofoil nomenclature, aerofoil definition, start looking at it. And then look for the homework number 1. Okay? Then we will go from there. All right? So we are going to finish today on time. Starting Wednesday, please come on time because in the beginning I do a lot of announcements, questions. Don't come late, please. Okay? Thank you all. See you.